Welcome to our afternoon session. My name is Christian Kaufmann and I'm your session chair. Our first speaker is Mr. Sreenidhi Ramadurgam, and he is talking about when ransomware fails. Sreenidhi is working at Cisco and has quite experience with cybersecurity and ransomware.
Hello, good morning everyone. Thank you for attending my talk. Thank you, Rene, for giving me this wonderful opportunity. I'm Sreenidhi Ramadurgam, security researcher at Cisco. Apart from work, I conduct workshops on malware analysis at universities and colleges across India. I'm a GRIM certified malware analyst. I watch a lot of animes and I'm a huge fan of One Piece anime. I have mentioned my Twitter handle here. You can get connected there. In this talk, I'll be speaking about the ransomwares, what they do, and where they can and cannot encrypt. This is my today's agenda for the talk. We'll see what exactly is a ransomware and how they can enter into our systems. We will look into how these ransomwares can find the files within our logical drives. We'll look at the encryption flow that is common to every ransomware out there. And in the end, we'll see a scenario where most of the ransomware fails to encrypt with a simple trick. So before we dive into the juicy stuff, what exactly is a ransomware? Ransomware is kind of a hostage situation where an attacker holds the files as an hostage and keeps them encrypted until the demands are met. However, even if the user or the organization complies with the attacker's demands, they may or may not get the decryption keys. So in simple terms, a ransomware is just a program which can encrypt the files and demands for ransom. Ransomware has caused havoc around the world in the last few years. WannaCry is the prime example of this. The attack was estimated to have affected more than 200,000 computers across 150 countries, with a total damage ranging from hundreds of millions to billions of dollars. In the last year alone, around 81% of the UK healthcare was hit by ransomware. It has even led to loss of lives. It is estimated that around 265 billion dollar damage might happen in the next decade. The damage occurring through ransomware is unimaginable. We have seen loss of money, loss of business, loss of lives. It is just the need of the hour to protect against the ransomwares. Ransomware has become very sophisticated in the modern world. Just like how every company has the business model, threat actors also has developed a model for ransomwares. Just like how we have software as a service, where the application is installed in the cloud and made it available to the users. The same way, ransomware are also being offered as a service these days. It is simple. It's just like pay it and use it. You pay for the ransomware and you can use the ransomware. Anyone can go into the site in the .NET and create an account. Of course, in order to run the ransomware, one has to pay the money in the form of a cryptocurrency. Generally, threat actors prefer bitcoins. Each time the user of the service makes money, a cut goes to the threat actor who's running the service. So, what is a ransomware to an attacker? In many cases, the attacker is a developer here. A ransomware is just an application to an attacker. It's just a program which can do a particular task. And what is the task here? Encrypt the files and demands for the ransom. If a program can encrypt the files in the system and demands the user for the ransom, then that can be a ransomware. So mainly it should have two parts. A code that encrypts the files and the node that asks for the ransom demand. So any other Any other task that it does would be an additional functionality or the feature that is added to the ransomware. These days, ransomware checks for many things in the victim system before encrypting the files. Sometimes it might hide in the system for a very long time and then execute the encryption part. It can even send the victim's data to the command and control server. Sometimes it does not execute the encryptor function due to the analysis tools like debugger, workshop, process monitor, etc. within the system. So these are all the additional features or the functionalities that it can have, just like how an application has the features. So ransomware enters into the victim system in many ways. Most popular ones are malvertising, spam emails, drive-by download. In malvertising, the malicious code is injected into the ads. When the user visits these ads, a malware can be dropped into their system. Or an email with a malicious attachment or a malicious link is sent to the user. When they execute the malicious attachment, the ransomware might be dropped into their system. Downloading the file using a link corresponds to drive-by download. As we discussed just now, emails are one of the most popular ways for a malware to enter into a user system. Usually, the user gets an email with an attached document. Then the document is downloaded in the victim system. When the document is open, the user gets infected. This document might be a downloader or a dropper. A downloader will have a malicious link from where it can download the executable payload. A dropper will have an executable file embedded inside the document itself. This executable file can directly be a ransomware, or this file can download another file which could be a ransomware. This whole attack methodology basically depends upon the attacker. An example of such is an exorist ransomware. In this case, the document directly drops the ransomware. This is a technique where some content is encoded using the XOR function with a key. As you can see here, this is the encoded content here. An XOR decoder is placed in the code to decode the content. This is the XOR decoder. The decoded content is a PowerShell script which can download an executable file and runs it in the victim system. After decoding this, we got an PowerShell script here. The executable file is the ransomware in this case. This methodology is used in exorist ransomwares. Now let us see a typical scenario where ransomware is a result of multi-stage compromise. The attack usually starts with malspam, malicious emails usually added in active thread or email chains. A web link leads to the malicious document, weaponized with exploits which launches the malware. Here the malware can be emotet or sniff or any other ones. I've taken an example of emotet. The initial loader disables all the security controls, establishes persistence, and downloads additional malware in the system. When all the targeted data is exfiltrated, another malware like TrickBot is downloaded and launched. TrickBot proceeds to take control of the domain controller via SMB exploit or any other exploits, which can lead to a network compromise. The last step in the infection chain would be the ransomware, which will encrypt all the affected components. Here, as ransomware is evolved, tactics and threats are also evolving. So we have two types of propagations. One is manual propagation and the other one is automated propagation. In manual propagation, threat actors will run the encryptors, deploy the encryptors using batch files. They can deploy the same encryptors with GPOs, that is Microsoft Group Policy Objects. They can also deploy these encryptors using a software deployment tools utilized by the victim organizations. in automated propagation. Credentials or the credentials or Windows tokens are extracted from the memory or the disk. The trust relationship between the systems. So they use this relationship, the trust relationship, that is like they can use WMI, SMB, or PSEXAC to bind the system and execute the payloads. Sometimes they also use unpatched exploitation methods. That is, for example, they could use eternal blue. Okay, so in Windows systems, the disk have partitions. Each partition can have a file system format. We call each partition as a logical drive here, and we can store the files in these logical drives. Here we could name these logical fields with any string, but in general, all the logical drives has a letter assigned to it. You see that it generally starts from C. Any letter from A to Z can be assigned to that drive, logical drive. The C drive has all the operating system files and the application files. Back when floppies were a thing, A and B were the letters assigned to the floppy drives. Since floppy drives has become obsolete now, we do not see A and B letters being used anymore. But we can always assign them to a normal partition or normal logical drive manually. Since OS will not do it automatically, we'll be doing it manually every time if we want to assign A and B letters to a drive. Okay, so now let us assume we are zipping a file with a password manually through UI in the Windows system. How do we go about this? First, we have to open a computer, and as we see different drives in the system, like C, D, E, we have to choose a drive. Once we are inside the drive, we have to choose the type of the file. We have to choose the files. Once we choose a file, we can zip it or encrypt it. This is a basic flow for any normal user. Now let us see how ransomware does this. It also checks for the drive first. It finds the file in the drive and then encrypts it. The flow is always same here. Now let us look at some of the ransomwares, what they do in the process of encrypting these files. The first example we'll be looking at is the WannaCry. Everyone here probably knows about this infamous ransomware. It uses the eternal blue exploit to spread inside the network. It uses some commands to grant permissions to the files that it has created. Uses a combination of RS and ES algorithm to encrypt the files. It is particular in targeting the files and also uses the Tor to send the encryption keys to the CNC server, that is the command and control server. It also kills some of the services in the system so that it can encrypt the data. And these are the file extensions that are targeted. So it will ignore anything other than these file extensions. So to analyze a malware, we have used IDAPRO tool here. IDAPRO tool is a decompiler and also a debugger. The screenshot that you see here is taken from IDAPRO. All the executable files running in the Windows system will use different API functions for different tasks. So there are these are the predefined system library functions. Here, in order to get the number of logical drives present in the victim system, it uses Win32 API function. The function name is get logical drives. So as we saw before, for encrypting the files, first it has to get the drives first. So for that, it is using the get logical drives. When this function is called, it gives the drive letters as the output that are assigned to the drives. It also checks for the drive type. For that, it uses get drive type W function call. Threat actors might not want to encrypt all the different type of drives present in the system. So they use this function to find the type of the drive. The output of the function will be a number. Each number corresponds to each type of drive. For example, as you can see here in the screenshot, there is a compare instruction present below the get drive type W, which is comparing the output to the number 4 here. The number 4 corresponds to the network drive. Interestingly, when I ran WannaCry sample, it did not encrypt the files which are there, which are present in the drive A or drive B. As you can see in the screenshots, on the left, we have the files in the drive A, which are not encrypted. On the right, we have a drive H, and the files are encrypted. And the file extensions has been changed to .wncry. Operating system did not assign the letter A here. I have done it manually. So why is this happening now? Why the WannaCry ransomware is not encrypting the files which are there in the drive A or drive B? So when we look at the code of the WannaCry, we can see that it only checks for the drives starting from C to Z. So the get logical drives function might give you the letters A and B if they are present. But the latter code in the ransomware does not bother to does not bother about these two drives, even though if they are present. Since it does not check A and B, all the files which are there in the drive A or drive B will be intact. Ransomware will not touch any files which are there inside those logical drives. Coming to PISA ransomware, this is mainly used on healthcare providers, government agencies, and managed service providers. Similar to every other ransomware, it checks for the logical drives. This ransomware will not use persistent mechanism on encryptors, but it uses persistence on ransomware node, so that the ransomware node pops up even when the victim reboots the system. When we run PISA ransomware, first it checks for the mutex. Malware uses a mutex to avoid infecting the systems more than once. If the mutex is not present, it creates a mutex with a string called PISA. Suppose if the mutex is already present in the system, that means the file might have been running in the system at that point. If we run another instance of this ransomware, it will exit from executing in the system, because ransomware thinks that when another instance of the ransomware is already running because it's not the mutex. This way, if we manually create a mutex in our system without running the malware or the ransomware, even though we run the malware after that, or the ransomware after that, it may not encrypt the files, because the malware will think that like it sees the mutex, so it thinks that it is already running inside the system. PISA ransomware also checks for the drives. Here it uses a different API function, that is get logical drives string W. So like we saw a different API function, that is string logical drives. This is a different one to find the logical drives present in the system. The function is similar to get logical drives that we saw in WannaCry. The only difference is in the output of the in the format of the output. This function also gives the drives that are present in the victim system. Then this PISA ransomware also checks for the type of the drives using get drive type W. As I have mentioned before, get drive type W will give the output as a number, and each number corresponds to a specific type of drive. As you can see here in the second screenshot, the output of the function is comparing to number 3. And number 3 here indicates the fixed drive. So in this case, Only when the drive type is fixed, the PISA ransomware will encrypt the files which are there in the logical drive. Dark side ransomware, uh, dark side ransomware attack has caused a shutdown of colonial pipeline. This group is operated as a ransomware as a service. It uses Tor for C2 communications and exfiltrates data to the command and control server. There were cases where they led to double extortion. Dark side ransomware will also delete the shadow copies. This is done by using a PowerShell script. Initially, it was obfuscated. When it is decoded, you can get the command that deletes the shadow copies. Also, this is done in WannaCry 2. Again, same thing with this sample too. It calls the get logical drive string W to find the drives present in the system. And then it checks for the drive type. If the drive is of particular type, then the drive letter is passed to a encryptor function. The encryption function encrypts all the files in that drive. This happens in the form of a loop until it encrypts all the assigned drives in the system. The last ransomware that we are going to see is the Phobos. It uses AES-256 and RSA-1024 asymmetric encryption to encrypt the files. It is delivered through emails, stolen or exploited ODB sessions, or it has used software vulnerabilities for the initial access. It is seen that there are like many similarities between Phobos ransomware and the Therma ransomware. In the new sample of Phobos, it is using the fileless technique for their vision. Again, same story with this sample too. It calls the logical drives W to know the drives present in the system. It places the output in a variable. Later, for every few seconds, it again calls the same function, that is get logical drives string W. This output is compared with the previous one. This way, the ransomware will know if any additional drives has been added to the system. For example, if a USB stick or an external hard disk is inserted in the system, it is also considered as a logical drive. So a letter will be assigned to that drive by the operating system. Since ransomware calls get logical drive string W constantly for every few seconds, it will come to know that an additional drive has been mounted in the system, and the encryptor function will run on that drive too. So all the drives on the USB stick or on the external hard disk will also be encrypted. This runs in the form of a loop endlessly as a separate thread. Coming to API functions we have seen till now, we have seen two functions being used by the ransomware to find the logical drives. They are get logical drives string W, and the other one is get logical drives. The function get logical drives string W, it fills a buffer with a string that specifies a valid drive in the system. That means if the C, D, and E drives are present, the output will look like this: C:/null byte, D:/null byte, and E:/null byte. This will be the output of this function. Another function that we saw for knowing the drives is get logical drives. It retrieves the bit mask representing the current available disk drives. For example, the output might be in hexadecimal, like 8C. When we write this in binary, we get some zeros and ones. So we can map these zeros and ones to the alphabets and compare them. One means the drive is present at the particular for the alphabet, 0 means drive is not present. So as you can see here, A has 0, that means A drive is not present. B has 0, B drive is not present. But for C, D, and H, it has 1. So that means only these 3 drives are present inside that system. As we saw earlier, for knowing the type of the drive, the function get drive type W is used. When this function is called, it determines the type of the drive. So if the output of the function is 2, then it means the drive is removable. The output is 3, then it means the drive is switched. 4 indicates that the drive is a remote drive, that is the network drive. With this info, the threat actors will decide for what type of drives they want to encrypt the files. Like, remember that they always do not want to encrypt all the files which are there in all the drives. So sometimes they might not want to touch the CD drives, or sometimes they might not want to touch the removable drives. It totally depends upon the threat actor. Now let us look at the general flow that has happened in the ransomwares that we saw till now. First, it gets the logical drives using an API function, that is get logical drive string W or get logical drives. Then it will find the files present inside the logical drives. This is done by calling another Win32 API functions. Then it will encrypt the files. Now we will see a simple trick where most of the ransomware fails to encrypt the files. Reiterating this again, we have a disk and it is made into few partitions which are called logical drives. Each logical drive will have a label, or it will also have a letter assigned to it by the operating system. As you can see here in the first screenshot, we have 5 volumes here. Volume 0 to volume 4. Volume 0 to volume 4. Volume 1 has the letter C assigned to it. We will not, we will have, volume 1 has the C letter assigned to it. We will have all the system files in this volume 1, that is in the drive C. I have made the other 2 partitions here, that is volume 2 and volume 3. And volume 0 is not a partition, but it is associated with the CD drives. Volume 3 and volume 2 has the letters E and H associated with it. Ignore the volume 4 here, as it is just a hidden partition made by the operating system for recovery and stuff. As we know already, when we run the ransomware, first it calls the Win32 API function like get logical drives string W or get logical drives to find out what are the drives present inside the system. When it is called, the output, in this case, the output will be C, D, E, and H. Now let us do one thing. We will remove the letter associated with the volume. We'll remove the letter E. The volume or the partition will still be present. It will have the same NTFS or any other partition that that is existed, and all the files within that partition will still be present in it. The only thing that is missing is it does not have a letter assigned to it. The same thing is shown in the second screenshot. The volume 3 does not have a letter assigned to it. So I have removed the letter E. So it has a label new volume, it has a NTFS partition, it has the volume is like healthy and like working. But the only thing that is missing is the letter assigned to it. Now let us run the malware again. The ransomware, when the ransomware runs, it calls those API functions which gives the drive letters. Now here comes the trick. When you look at the second screenshot, you can see that there is no letter assigned to some volume. So in this case, the output of the function will only be C, D, and H. It will not give you E, as E is not assigned to any logical drives here. So ransomware encrypts all the files which are there in the C, which are there in the H, and sometimes in D too. Since it does not know that there is another partition present, it cannot access that drive. So E is not present, so it cannot know that there is another volume without a letter assigned to it. So all the files present inside that partition or that volume 3 will still be intact. This is the scenario where most of the ransomwares will fail to encrypt the files. So why is this happening is like, since it cannot go inside that particular volume using using a drive letter, so it cannot encrypt any of the files which are there in the system. So all the files which are there in that particular volume where it does not have any letter assigned to it will still be intact. We will see a demo where we ran a Paisa ransomware and it did not encrypt any of the files when the volume is unassigned. So we have a new volume called E here, and there is ABCDEF volume drive. The letter is assigned is H. So we have H and we have E. So what I'm doing now is we are checking out what are the volumes that are present inside the system. So we have D, C, H, and E. Now I'm selecting a volume here. I have selected the volume 3, and the letter assigned to that volume 3 has been removed. Now, as you can see, there is no drive that is present here. There is no drive called E that is present here. Only H is present, C is present, and D is present. Now, I'm going to run. Now I'm going to run a Paisa ransomware here. So I ran the ransomware. Now let us look at the files if they are encrypted or not. In the drive H, all the files are encrypted. In this folder, all the files are encrypted, and it has an extension of .paisa. Now what I'm doing is we will check if the files in the unassigned drive is encrypted or not. For that, I'm assigning the drive again. Sorry. So I'm going to select the volume 3 here. That is the drive. That is the volume that is not assigned. So after that, we'll see if the files in that volume is encrypted or not. Selected the volume. I'm going to assign a letter E to that particular volume. So it has been assigned. As you can see, there is a volume here. So as you can see, a different one here, like an additional drive has been added, new volume, drive E. If we go inside that function, so these are the files that are encrypted inside the drive H. But when you go into the drive E, all the files which are there here are still intact. So this is a screenshot taken after infecting the files with Paisa ransomware. As you can see here, it did not encrypt any of the files which are there in the right hand side. So all the files here within the unassigned drive will still be intact. This is another screenshot I have taken by running the .site ransomware. It also did not encrypt the files if the drive is unassigned. This sort of behavior is happening because in the ransomware, there is no code to check the drives which does not have any letter assigned to it. The API calls will it only gives the letter of the drive as an output, as it indicates the logical drive. Since the threat actor are not checking the remaining partitions, all the files which are there in the unassigned drive will still be intact. For each partition or volume, along with the drive letters, we have a volume ID too. You can access the files using this volume ID instead of a drive letter. As we saw in the case of Phobos, it checks for the drives constantly even after encrypting the files. This way, when a USB stick or external hard disk is inserted, Phobos will know that there is an additional logical drive has been mounted. So in this case, if the unassigned drive files will be, sorry, in this case, the unassigned drive files will also be encrypted when we assign it to access tab. We can use volume ID instead of drive letters in order to access these files, which are there in the unassigned drive. This way, we don't have to assign the drive when it is needed. An example of copying the files using the volume ID. Instead of in the first screenshot, I have used drive letter to access the files. In the second screenshot, instead of using the letter E to mention the path, I have used volume ID. So I have copied a text file using the volume ID inside the drive. This way, we don't have to assign the drive. We don't have to assign the drive to copy the files or the access the files which are there in the unassigned drive. Just like, as it a matter of keeping the additional code inside the ransomware, in the future, attacker can write a code to assign a drive before running the encryptors. Or they can use the same volume ID concept, so instead of using the drive letters. I have tested this scenario on many ransomwares like WannaCry, Paisa, DarkSide, Phobos, Ryuk, Dharma, Exorcist, Maze, and so on. None of these ransomwares will encrypt the files if the files are present in the unassigned drive. Well, the question is there any ransomware which can encrypt the files even though the drive is unassigned? Unfortunately, the answer is yes. I have seen one ransomware which was like released very recently, that can encrypt all the files regardless of if the drive is assigned or not. Logbit 2.0 is a ransomware with this feature of assigning all the volumes in the victim system. This came out in the end of August or the beginning of September 2021. This is a very recent one. This is the only ransomware I have seen till now with this feature. What it does is very simple. Before finding the drives, first it forcefully assigns all the logical drives present inside the system. It will also assign the hidden partition, which is present inside the Windows system. That is the recovery partition, which we just ignored. The flow will be like this. First, it assigns the logical drives. After that, it finds the drives. When it calls the API functions now, it will get all the logical drives because it has assigned the letters to the logical drives before calling that function. So after that, it finds the file, and then the encryptor function will run on those files to encrypt those files. This way, it will not miss out any files without being encrypted. As it is just a matter of time for all other ransomware to keep this up. So even other ransomwares can adopt these features like accessing the unassigned drives by assigning the letters to it. in the end, it is just like a cat and mouse game where we must be updated every time when the threat actors comes up with different ways to compromise our systems. With this, I conclude my talk. Uh, Please let me know if you have any questions. Thank you.
Thank you, Sreenidhi. Um, The first questions, my first questions you already answered. My first question wouldn't be an easy task for the ransom developers to access the drives based on the volume ID, and you said this will be the future. May I ask in the room, are there any other questions? No, but I have one, because if I have here one ransomware expert, I would be interested in your opinion about international ransomware groups. Yeah, they are decreasing at the moment, but the amount of successful attacks are increasing. For most companies, ransomware attacks is a thing now, and they try to improve the countermeasures. So I would like to pick your brain on the question: do you think, because of these countermeasures, the attack of the ransomware groups will get more sophisticated in the future, or will the ransomware groups focus on low-hanging fruits?
Definitely, the attacks will be more sophisticated. As like I spoke about ransomware as a service, right? It is the state of the art like mechanism. As a software as a service, they're running the ransomware as a service. They're like handing out the ransomwares and they're getting the payments in that form. So definitely, the attacks will increase in the future, and we have to be prepared for that.
Yeah, well, if they get more sophisticated, then they will attack the drives based on their volume ID, as you mentioned. Thank you.
Yeah. It's not only the volume ID, I spoke about the ransomware called Logbit 2.0. This was released recently, and this is also a ransomware as a service, and it is actually assigning every drive which is there inside the system, and encrypting all the files which are there in the logical drives. So this is also one of the functionality, and I think in the future many of the ransomwares might adopt this functionality to assigning all the drives regardless of what they want to encrypt.
Okay, thank you very much.
Thank you.
Are there any other questions? No, then thank you.
Thank you.